click somewhere. Oh yeah, okay. Okay, so hello everybody. As Kasia said, this is our recent work about the Q-voter model, basically. And in the title, it states that the model with anticonformity, but I decided to go through the whole process step by step. So the model with the independence also will appear in this presentation at the beginning, to easier to follow for you and for me, I hope. So we will start with the binary model itself, so the basic one. Then we will switch to a multi-state model with independence. Then I will check what will happen for the model with anticonformity. And at the end, if the time will be helpful for us, I will say something more about the trajectories, spinodal lines in this model. We will discuss it later. Okay. So at the beginning, we will assume the very basic model. So the binary one, in which agent can perform one of two values, -1, 1, 0, 1, yes, no, you can denote it as you like. And you can track the state of the system by the average opinion. So basically the proportion of positive agents among the whole system. And one question, do you see my cursor when I'm moving around it?
Yes, yeah.
Yes.
Great, great, thank you, thank you. And based on this concentration, you can distinguish some phases when you look at the stationary values of your model. So basically, you can distinguish order phase when the concentration is different than 1/2, and disorder when it's equal. And this is what we basically will try to do. So distinguish how the transition between order and disorder phase overcome for specific model itself. And I will look on the spinodal lines. So basically two critical points, let's say. One is P1 star is a lower spinodal line, which basically show me the place at which the disorder phase changes from unstable to stable one. And the upper spinodal line is the line at which, for the discontinuous phase transition, the jump of the concentration on order parameter appears here. And in the continuous case, these 2 points are equal to each other. And in the discontinuous case, they can differ. So basically, we see that this additional unstable region, and we can switch, when we look on the flow in the system, we can switch from one stable solution. When we move with initial condition below this unstable region, we can move to disorder, basically. So we are like the coexistence of the phases here. We also will be looking how some different randomness types will influence our model. So I will distinguish 2 types of this randomness, annealed one and quenched. Annealed one will be the situation in which properties of agents varies in time. So when I pick an agent, he can act in one way, but when I pick him again later on, he can act in a different way. And we will deal with this varying time with some probability. So this agent will act with some probability in a given way. And the quenched randomness is basically the situation in which I set the behavior of an agent. And this behavior will be exactly the same for the whole simulation. If the agent will be set up as the, I don't know, the independent one, he will be the independent for the whole simulation. And we can connect these 2 randomness types with some social psychology terms like person situation debate, in which we can distinguish between 2 behaviors of the people. Like we can have some our beliefs, some behavior, our personality, and we can make decision based on that. Or we can make our decision based on some circumstances around us, like, I don't know, our friends try to influence us or something like that. Okay, I can track everything analytically because I will show you today only the case of the complete topology. And the next week we'll have presentation of Arek, and he will show us more about different networks. But today I will focus mostly on the complete graph, so everybody is connected to everybody. Thus, I am able to track everything analytically really well with a mean-fit approach. But also, I want to make a Monte Carlo simulations to check my calculations and to look more deeply how the model behaves in real let's say, in real. And one thing which is quite also important to notice is we will be dealing with the asynchronous updating. So one agent can change at given time, which in contrast to synchronous updating, in which all agents can be updated at the same moment, so simultaneously. So one agent can be updated on one time. So I can write, thanks to that, really nice rate equations later on. Okay, so first let's look on the annealed version of the Q-voter model. So picked agent can, with probability P, act like the non-conformist, and with probability 1 minus P as the conformist. And in the non-conformity case, we can distinguish two cases, anticonformity and independence. And right now I want to describe it really briefly for those who are not familiar with this model. So in the conformity case, the chosen agent, so basically this one, AI, he can have one of the opinions -1 and 1 because the model is binary. He look on his neighborhood and draw randomly Q agents from this neighborhood. And this will be called the chosen Q panel, the unanimous Q panel. And unanimous because he look if this panel agrees at some point. So for example, they 4 agents, so my Q is equal to 4, agrees at value 1. So thanks to the conformity, my agent will also apply this value to himself. And this is exactly the same in the opposite case. When the neighborhood is agrees on the value -1, I'm also apply -1. When I'm dealing with the model of independence, I just flip a coin. So I pick one value, one of the values, so 1 or -1 with equal probability 1/2. And in the anticonformity case, I look on my neighborhood in a similar way as in the conformity, but I will apply opposite value to this neighborhood. So I want to be different than my neighborhood, basically. And in the case when the neighborhood is on value -1, I do the same. And when I look on the results of the binary Q-voter model with independence and the anticonformity, it turns out that for the anticonformity, no matter of the value of Q is, I obtain the continuous phase transition all the time. And when the independence takes place, we start to observe a discontinuous phase transition where Q is above some certain level. And this level is Q equals to 5. So when I have Q bigger than 5, I start to observe the difference in spinodal lines, basically. So lower spinodal line is different than upper spinodal line. What is in contrast to anticonformity case when they're equal. And then was a question, what will happen if I will change the type of randomness? Because that was the result for the annealed case. What will happen if I will have the same model, but the quenched randomness? So basically, I take my whole network and with some probability P, I will apply that this guy will be the conformist for the rest of the simulation. And this guy will be the non-conformist for the rest of the simulation. So this time, this P will describe the fraction of non-conformist agents in the system in some sense. And when I pick an agent to make an influence or to make a flip, he will look what is his behavior. If he is a conformist, he will apply the conformity rule. If he is an independent one, he will apply the independence rule. And or he is anticonformist one, he will apply the anticonformity. And this rule is exactly the same. So the basic difference is that right now agent has set behavior, but previously he decided with some probabilities. This is the only one change in this model. And what it appears that for this model, anticonformity gives exactly the same result, and independence destroy all discontinuous phase transition, and we obtain quite similar behavior to anticonformity one, but it scales by some constant, so we obtain bigger values here. And in this case, spinodal lines are equal for both of models, and they are the shape of this curve is pretty much similar. And then we can ask the question, and this is what we did in our work in the previous year. So what will happen if we have these two types of randomness, but instead of binary model, we will include more states into the system. What will happen if we have, for example, 3-state model, 4-state model? So I will have S-state model right now, and I will denote it each state with value 0, 1, 2, etc. up to S-1. But once again, you can denote it as you like. It doesn't really matter. This is just easier to track for us analytically and with description of the model. So that's I will do it like this. And again, I'm able to track the behavior of my system of the concentration. And this concentration can be calculated for each state in the system. So basically concentration 0, so C0 will be the number of agents in state 0 among the all agents in the system. And these concentrations for all states can be really easy calculated. But what we think it should give us in the future, so what will the outcome of this change should be? And when we look in the history, so for example, on the Potts model, which is the generalization of the Ising model, it appears that if the number of states is bigger than 4, we start to observe the discontinuous phase transition. We start to observe jumps on hysteresis. But for example, for the majority model, in which we look on the whole neighborhood and my agent flip to the value which has majority in this neighborhood, so more than 50% of some agents will follow some idea, I will also follow this idea. So this is the majority rule. Only 3 states will change the behavior of the transition from continuous to discontinuous one. And when I look on this picture, also I can observe one interesting thing here, and this additional line between these 2 lines. One line describes the situation in which all opinions are equal, and this one when one opinion wins among the others. So what is this? And we can track this really easily with the intuition, let's say. So for example, when I have binary opinion, I can have situation in which concentration of -1 is bigger than 1. The second situation is the opposite. And the third situation is when they are equal. But basically, we can distinguish 2 cases, when one opinion is dominant, and the second case is when they are equal. And we can do the same for the 3-state model, for the model with 3 states. So one opinion is dominant, the 2 opinions are dominant, and they are equal. So we can really easily, by the induction or deduction, guess that we will have more stationary states if we have more states in the system. And we can write it in really easily because we will have S stationary solutions basically. And one of the stationary solutions will be the situation in which all opinions are populated equally. And these solutions in which 2, 3, 4, 5 opinions are dominant, are equal, are basically the saddle solutions. So from the wider picture, the bigger picture, I see that the solution in which one opinion wins among the others is the attractive one. And that also we prove for the model of independence, and I will talk about it in a minute. And all concentrations for state 0, state 1, up to state S-1 can be described by one variable. Let's call it C. And C will describe, for example, the concentration of state 0, and all other concentrations can be expressed with this C. So we can draw the picture in which we will only use this C. And I will do it with the rest of the picture in the presentation. And here I also am able to distinguish 2 phases, order and disorder, where disorder is again the situation when all opinions are equal, and disorder and the order is situation when one opinion is dominant among the others. And how the model looks like in the multi-state case. So independence is exactly the same, but instead of flipping a coin, I pick one of possible S states with equal probability. So I have uniform distribution among these states. And the conformity case also is exactly the same, but I have more possibilities because I can have neighborhood in the Q panel which agrees on the value s-1, for example. So my agent also will pick a value s-1. And what the outcome was, I calculated everything analytically, made the simulations, and we obtained this kind of pictures. So for example, for free-state Q-voter model with independence, in the annealed and quenched case, so in both cases, we observe a hysteresis loop, so the discontinuous phase transition itself. And what we can see here, that in annealed case, the hysteresis was much bigger than in the quenched case. So this quenched was quite close to the intuition from the binary model that we should have the discontinuous phase transition, but this increasing of the dimensionality of the system, so increasing more states, will cause this discontinuity, but it's much less sharper than the annealed case. And also what we can see, what was quite important, in the binary case, we need to have a big enough group of influence to cause the discontinuous phase transition. But when we include, for example, just one more additional state, this Q even doesn't matter. I can pick Q, arbitrary Q bigger than 1, and I will always obtain the discontinuous phase transition, basically. And this is true for both models. And for given Q, when I pick one of the Q, I see the more states in the system, the hysteresis is bigger. And this is true also for both versions of the model. And we can ask the question if it's easy to back to the previous model, so the binary version, and it is, because we are able to track everything analytically, and we see that the, for example, formula for the lower spinodal is quite simple, and dependence on the number of states also visible. So I can back to the binary case, and I exactly reproduce the solution for the binary model. So this, everything is clear. And what is quite interesting in the quenched case, the lower spinodal is always the same, Q-1 divided by Q, and this is exactly the same result which was for the binary model. So that is quite impressive and important, because when we look closer, so for example, when I put Q equal to 2 and check different number of states, I will observe that indeed the lower spinodal is exactly at the same point every time, but the upper spinodal is moving. So basically this moving of the upper spinodal will cause this existence of this coexistence region here. So that was our previous results from many papers and many discussions, let's say. So really quick summary, independence in binary case for the annealed model caused the discontinuous phase transition. Independence in binary quenched case destroys the discontinuous phase transition. But if we apply into model with independence more than 2 states, at least one more. So for example, we have model with 3 states. In both cases, quenched and annealed, we observe the discontinuous phase transition. And we want to ask what will happen with model with anticonformity. Because model with anticonformity acts quite differently, because in both annealed and quenched case, we observe only continuous phase transition. So the question is, if I will introduce more states into model with anticonformity, I will observe the discontinuous as well as the model independence. And that was our question, basically. And the first, let's say, problem was how to introduce the anticonformity in the, let's say, symmetric way to have some similarities to the previous model. So the idea was, let's look at the state of my agent, the picked agent. He will look on his neighborhood, and if he is the same as his neighborhood, I need to pick different value than my neighborhood, because I want to be different. Because if my value will be, for example, 0 and the neighborhood will be 1, I am different, so I don't need to change. But if I am the same, I need to pick one of the remaining values. And I have s-1 possibilities. So each possibility is equally probable to pick. So basically, I pick one of s-1 remaining solutions. And the conformity is exactly the same like previously. So if the neighborhoods have some opinion, I will apply this opinion to myself. And what we did, we calculate everything analytically, make a Monte Carlo simulations, and similarly to the majority vote model and model of Q-voter with independence, we observe additional saddle solutions. So this black line where two opinions are dominant among the third one, and also the solution when one opinion is bigger than the two others, and also the solution when they are equally populated. So we have, again, for example, for three-state model, we have three stationary possible solutions. And I make Monte Carlo simulation, check this for all possible S values. Of course, S can go to the infinity, so I cannot check everything, but I check most of them, so as many as possible to make it by hand, for example. And I observe only continuous phase transition with model with anticonformity, only. No matter what was the value of Q, no matter what's the value of number of states. And when I calculated the lower spinodal, I obtained such equation, which is quite easy to reproduce the binary case, because when I put it S equal to 2 here, I will observe exactly the same value as in the binary model. And again, upper and lower spinodal are equal. Sorry. And when I look on the whole spectrum of number of states here, I will observe that in no matter what the number of states, no matter what the Q, the spinodals are equal, and the behavior of the model is quite similar. They are only somehow scaled. And so basically, this is the first difference. In the model with independence, more states causes the discontinuity, but here's not. So we ask the question again, what will happen if we do the same but with the quenched model? And this is the case. We did it and we calculated analytically again and make the simulations. But in this case, to track everything, we should introduce more equations. So for example, so basically the equation for the concentration of anticonformist agent in state alpha and conformist agent in state alpha itself, and we can join them together by this equation. So again, I can produce the concentration of agent in state alpha very easily, and this active forces will be used later on. That's why I show you these equations here. So I can calculate everything and reproduce the solution. And what happened? It happens that in the model with anticonformity Quenched version happens something strange, because we obtain the discontinuous phase transition for more states, even for one additional states here. And this is in contrast to the knowledge which we have right now about this kind of model, because Quenched typically destroy the discontinuity in these models. But here for the model with anticonformity, we have switch behavior. So Quenched model produce discontinuity, but Annealed not. And basically, I could finish at this point, because this is the main message from our work, but I will not, because I have something more to show you, which is quite cool for me, and I hope for you also. Because I make a simulation to track the hysteresis itself. So what we have here, the lines are obtained from the mean field approach. So basically this lines like here, and points are Monte Carlo simulations itself. So when I simulate from the initial condition when one opinion is dominant, so for example, C0 is equal to 1 and others are 0, I have perfect match with upper spinodal. Everything lies perfectly, it's great. But when I do the same to track the lower spinodal, something crashed. I have the simulation line here. What was quite strange for me, because in the independence model with independence, the spinodals are reproduced with the Monte Carlo simulation perfectly. But we have problem here. And what to do that? So we can perform more complex stability analysis. And I hope most of you are familiar with that, but I want to point some important things. So when I have a system, and this is basically a linear system, so I can extract from this the Jacobi matrix with the derivatives over the over the effective forces, and I will show the calculations in a second, I can track the sign of the determinant and trace, and based on the signs, I can lie somewhere in this picture, this Poincare diagram. And then I will see that my system will behave in some way. So for example, when I lie here, I will have spiral sync. So I will converge to some solution in a spiral way. When I have these values of the determinant and trace here, I will be the normal sync. So I will just converge alongside these lines. And I did that. So I produce the Jacobi matrix, produce the determinant and trace, and I obtain some kind of equations like this. And what is quite important here for the model with anticonformity is that determinant is increasing with value of p, and trace is decreasing with value of p. And why this is important? Because they should somewhere cross the zero, somewhere, because one function is increasing, one is decreasing. They can be defined for the p from minus to plus infinity, so they should somewhere cross the zero. But I am interested in p between 0 and 1, in fact. So I do that first for the model of independence, and no matter of the value of q, no matter of the number of states, the trace is always negative. So it's good. Why? Because when I again look on this picture, when the trace is negative, I'm only on the left part of this picture. So the lower spinodal, so the moment at which I'm moving from unstable to stable regime with the solution when all concentrations are equal, is only defined by the sign of the determinant itself, because I can be here or here, because trace is always negative. But when I look on the model of anticonformity, this is not so easy, because there are some regimes in which trace are positive, in fact. So I have some triangles like that, when both trace and determinant are equal, are positive in sign. So basically, I have regimes when I will have maybe some oscillations, maybe some additional stable solutions not equal to saddle one. And I'm able to calculate this point, these 2 points here. So basically, the point at which determinant and trace will change the sign. But this is quite easy because I have the formula for determinant, so I can make it equal to 0. It's not tricky. What is cool here, the cool is like determinant is equal to the lower spinodal of the Q-Voter model with anticonformity in the binary case. And this is quite funny for me, especially. And when I check for my picture, when there are lay, so for example, this root of determinant is exactly at this point, which was reproduced by the mean field approach. And the trace is exactly at this point when my simulations break. So exactly, we have the answer. So sometimes the lower spinodal will be defined by the sign, by the value of the trace itself, by the root of the trace. So this is quite important. But I was thinking like, okay, I have mean field approach, so I can produce the picture CP. I calculate the stability analysis itself, and I obtain the picture that something is going on wrongly here. So I can check it differently to obtain a picture which will match with this trace and determinant. And I can, because I can take the pixel from this pane. So for example, 0.5 C and P035. And this will be my initial condition. So basically, I know that for P0.35, I will start with concentration equals to 0.5. So the dominant one will be 0.5, but the rest of the concentration will break another way. And I will check to what this analytical, I need to point it out, analytical trajectory will converge. And it will converge to this line. The above line, I will color with green. It will converge to the bottom line. So basically all concentration will be equal. I will color with pink. And I obtain this picture. So we see that this some kind of naive hysteresis matches with this trace. So everything with our calculations are okay, basically. Even if we do not see it at the beginning, because we see from the CP pane that this something is not okay here, but our stability analysis itself and the trajectory show us that everything is okay. So we can ask also the question, what's going on here in this regime between these two values? And we can look at the Poincare diagram itself and calculate the trace and the determinant for the values 1, 3, 1, 3, 1, 3, for example, when we have model with 3 opinions. And this will be the red dot. So the value of determinant for this solution, so this line here, and value of trace, and we'll lie here when we have p, for example, 0.35. So we are here. So we should obtain the saddle because we are in this regime of saddle solutions, and we are obtaining the trajectories exactly, which exactly behaves like the saddle solutions. And for example, for this regime between these two lines, we have solution which lays in the regime of spiral sources. So basically, we should obtain some oscillations in our system, and we see that these oscillations are visible, and they are diverging oscillations. So they should converge to something which is on the above level, let's say, and they will converge to this line. So this point is unattractive, and I will, in a spiral way, moving away from this point, and I will at some point finish at this above line here, and this is exactly the case here. And when I have this regime above, let's say the lower spinodal given by the trace star, I have damped oscillations, so I will, in oscillating way, moving alongside the value when all opinions are equal 1/3 in the case when we have 3 states. And these trajectories are obtained analytically, but also I checked, and Monte Carlo simulations also we observe this kind of behavior. I do not have a picture here, sorry for that, but you need to believe me that they are matched perfectly, so everything is correct. And we can do one thing more. So basically, how to decide when determinant is okay, when this root for determinant is okay, when the root for the trace is okay. And we can check that. So I know that determinant is always all the time increasing, the trace is all the time decreasing. So when the root for determinant is smaller than the root for the trace, then my region for which I will switch from unstable to stable solution, so-called lower spinodal, will be given by this pink region. So basically, if I am in the pink region, the lower spinodal is given by the P star trace, but when I'm in the green region, I'm given the lower spinodal by P star determinant, in fact. And when we look it for the binary case, it's perfectly connects with the original results when it's given by the P star determinant, in fact. So the result Q-1 divided by TQ. So this recovers also the previous solution, which is great. And we can plot it again in the pane when we have number of states from 2 to 5, for example, and some values of Q, and we observe that this hysteresis appears at some point, but when we start increasing the value of Q, it starts to decrease, what is quite also important here. But if we look to somehow connect these two results for Annealed model and the Quenched model, indeed the intuition was wrong. So for the Quenched model, we should obtain only continuous phase transition, and in the Annealed case, we might expect some discontinuity, but it was totally opposite. But when we, for example, colored this red regions here and only see on this as a green picture, and here on this green picture, these two models, so the Q-Water model of anticonformity in Annealed and Quenched case, are pretty much behave in a similar way, more or less. And that was all about our results. So we can somehow conclude. So basically, in the binary regime, model with independence shows us the discontinuous phase transition when the size of the group of influence was above some appropriate level. But when we include more states into the system, the discontinuity also appeared in the Quenched model, what was quite impressive. And for the model with the anticonformity, we have opposite situation, which is quite novel. So namely, the annealed model show us continuous phase transition, while the quenched model show us discontinuous one. And pretty much that's all. Thank you very much for your attention.
Thank you very much for the presentation and perfect time. So now we have time for questions. It's really rare that we didn't interrupt you, but maybe it's good. So maybe I will just stop our